That's actually hilarious.
So, I know, right?
Imagine a situation where you are holding your robot partner's lab robot's hands, and through your touch, your robot partner understands what you want. What you want exactly. I'm not talking about any intimate acts. I'm talking about just a simple, delicate touch, right? Can you imagine how does a robot gently handle a delicate flower without deflowering it? Now, don't take it otherwise. Deflowering means something else, I know also, but I don't mean anything else here. I just try to give you an example. And since we are talking about pressure sensors about our lab robots, humanoid robots, so we think that the magic lies not in the consciousness of your robot partner, but in the intricate world of pressure sensors.
Have you ever wondered what a robot feels? Not emotionally, of course, let's not get ahead of ourselves. But when a multi-million-dollar humanoid gently picks up a flower, how does it know not to crush the stem into green pulp? What phantom sensation travels through its metallic fingers? Is it simply following a command, a cold line of code that says apply 0.5 newtons of force? Or is something far more intricate at play?
Before we proceed, let me tell you one thing. If you have not subscribed yet, please subscribe. It means a lot to me. And if you have already subscribed, tons of thanks for your support.
The secret, my friend, isn't in some burgeoning robotic soul, but in the marvelous, maddening world of pressure sensors. It all begins with the hardware, the robot's very skin. Imagine a simple sensor, a piezoresistive one. Think of it as a microscopic sponge soaked in conductive ink. When you press down on it, you squeeze the sponge. This makes it harder for electricity to flow through, changing the electrical resistance. The harder the press, the greater the change. Simple, elegant, and beautifully effective, isn't it? Then there's its cousin, the capacitive sensor. Picture two tiny metal plates, separated by a squishy, rubbery gap. When force is applied, the plates get closer, altering their ability to store an electric charge, their capacitance. It's a whisper-sensitive system, capable of detecting the lightest touch, the equivalent of a fly landing on its finger. But a single sensor is just one note in a symphony. To truly feel, a robot needs a whole orchestra. So, engineers blanket a robot's hand in an array of these sensors, a grid of sensitive points. This creates a tactile map, a low-resolution image of the forces at play. Yet, this raises a thorny question, doesn't it? What happens if you press between the sensors? Is the robot just making an educated guess about the forces in the gaps? In a way, yes. Researchers are constantly chasing this ghost, trying to create a true electronic e-skin. Scientists at the University of Glasgow, for instance, have developed an e-skin that not only feels, but is powered by its own integrated solar cells. Imagine a robot that not only feels your touch but recharges itself from the light in the room while doing it. Now, let's move from the skin to the brain because this hardware only produces a chaotic flood of raw data.
It starts with the hardware. Basically, it's a hardware part. Of course, you know that whenever we think about any love robot, any sex robot, any robot partner, whatever you want to call it, you can call it, no problem. It is There are three distinct parts: hardware, software, and algorithms, right? So this is practically this practically belongs to the hardware section, because the robot's skin, which is often a grid of piezoresistive or capacitive sensors, it's very difficult to pronounce these things, you know, that translates physical force into electrical signals. That means whenever you touch a robot a certain point, again I don't mean anything particular point on its body, but I try to just give you an example. Whenever you suppose you hold its hands and just give some or apply some gentle pressure, so that pressure, that physical force, turns into electrical signals. This creates a tactile map of the object being held. That means if you hold its hand, if you hold anything else, that is different thing. But if you hold its hand, then and apply some pressure, then the tactile map of the object being held, that means the hand, is generated inside the robot's brain. That means robot's CPU. However, this raw data is really very noisy and chaotic. This is where software steps in, acting as a translator to filter out interference and meticulously calibrate what different levels of pressure actually mean. That means pressure could be different. Of course, pressure could be different. Some pressure, if you apply a gentle pressure, that is something. If you apply a pressure forcefully, that of course something else. So finally, what is the role of algorithms here? The role of algorithms actually here is algorithms use this refined data that software translates to act. Okay, so raw data to refined data to action. That is the three steps, and that goes from hardware, software to algorithms. Simple systems employ a force feedback loop. It calls force feedback loop. Constantly, it adjusts the grip to meet a programmed force value. Okay, but the frontier AI is in AI. Robots from companies like Boston Dynamics or any other companies, they analyze tactile feedback to infer an object's properties. That means whether it's soft, it is hard, or it is yielding something. And according to those soft, hard, or something else, it adapts their grip predictively, right? I know this is a very complex process. Of course, it is a very complex process. And when super intelligence will take over these robot partners, this will be more complex and beyond, in fact, our knowledge, not only knowledge, but also our apprehension, also our feelings, and we cannot apprehend what is going on inside, just like a black box, you know. So this rapid silent conversation between hardware, software, and algorithms is the secret behind the robot's ghostly gentle touch.
This is where the software, the great translator, steps in. The sensors scream in the language of volts and ohms. The robot must understand the poetry of pressure. The first job of the software is to act as a bouncer at a very loud nightclub. It has to filter out the noise, electrical interference from the robot's own motors, slight temperature changes that warp the sensor readings, random cosmic rays. All of this is junk data that must be thrown out. Without this filtering, a robot might think a gentle breeze is a crushing blow. Then comes the monumental task of calibration. How does the machine know what 1 pound of pressure actually feels like? It has to be taught meticulously by applying known forces and telling the software, this is what that feels like. Remember it. But does it remember perfectly? Does your bathroom scale give you the same reading today as it did 5 years ago? Materials warp, electronics drift. The software must constantly be recalibrating, second-guessing itself, living in a state of perpetual uncertainty, not unlike us humans. Finally, we arrive at the ghost in the machine itself, the algorithm. The hardware has provided a clean signal. The software has translated it into meaningful data. The robot now knows with reasonable certainty the amount of force being applied to a specific point. So what? This is where the true intelligence, or a clever imitation of it, emerges. The algorithm uses this information in what's called a force feedback loop. The robot is given a goal. Hold this egg with 1 Newton of force. It touches the egg. Its sensors report back 0.8 newtons. The algorithm computes the difference and tells the motors, squeeze a little harder. The sensors now report 1.1 newtons. The algorithm commands, ease up a bit. This happens thousands of times a second, a frantic, silent conversation between the skin and the mind. But this approach has a glaring weakness. It assumes the world is predictable. What if the object isn't a hard-shelled egg but a soft, yielding raspberry? An algorithm just aiming for a force target would turn it into juice. This is where modern robotics is making leaps. Companies like Boston Dynamics are moving beyond simple feedback loops and into the realm of artificial intelligence. Their algorithms don't just react, they learn and predict. By analyzing the tactile data in real time, the algorithm can infer properties about the object itself. The pressure is increasing, but my fingers aren't moving closer. It might reason, therefore, this object must be solid. Or, the pressure is changing in a distributed pattern, so this object must be soft and deforming. Are we programming intuition now? It's a beautiful, complex dance between the physical and the computational. The hardware provides the raw sense of touch. The software cleans and translates that chaotic input. And the algorithm uses that information to make impossibly fast and delicate decisions. So, the next time you see a robot perform a task with grace, remember the ghost. Remember the constant, high-speed dialogue between its skin, its software, and its algorithmic soul. It's not feeling in the way you or I do. And yet, is its meticulously calculated gentleness any less real to the flower it holds?
So that is it. Thank you for joining us on this journey. Let's continue this conversation in the comments below. If you like the video, please hit the bell icon to get notified, and don't forget to like with your friends, share, and subscribe for more insights. If you have already subscribed, tons of thanks for your support. It means a lot to me. And please consider signing up for membership zone to support Wooden Slate so that we can make it better and better. See you in the next video. Till then, goodbye. Take care and stay safe.